Hello everyone, welcome back. This module is a little bit different from the others in that it does not correspond directly to any part of the textbook. Partly, it is a continuation of inverse trigonometric functions at the end of Chapter 5, but at the same time, it is a preview of Chapter 7, especially 7.4 trigonometric equations. Why am I doing that? Well, two reasons. We went through inverse trigonometric functions, but we didn't go through a lot of motivation for that there because the most important application of inverse trigonometric functions is to solve trigonometric equations. But if we dump everything over to Chapter 7, then at Chapter 5, after going through inverse trigonometric functions, why this? This kind of motivational problem occurs there. So I'd like to take care of this. Now, the second reason, which is equally as important, is to make Chapter 7 a little bit easier by giving this preview and spread out the material a little bit. Because Chapter 7, especially the trigonometric equation part, is so intense, usually students are overwhelmed there. At least that was my experience. So what I usually do is spread it out a little bit and prepare students in advance so that they can do a better job there. And that's the purpose of this notebook too. So we are serving those two purposes. Okay, let's go over to inverse trigonometric functions. In order to do that, we have to start with standard trigonometric functions, sine, cosine, and tangent. Here is the graph of sine function. Going up and down like this is an odd function that begins from the origin 0, 0. This is the graph of cosine function now. Again, we are going up and down like a wave, but this is an even function, symmetric with respect to the y-axis, and the maximum is 1, and that happens to be the y-intercept. Now here is the graph of the tangent function. We have increasing function like this, but we have vertical asymptotes at negative pi over 2, pi over 2, 3 pi over 2, and so on and so forth. Because tangent is sine over cosine, if we picture sine and cosine functions together with tangent function, as you see over here, we have this kind of nice relation. We have vertical asymptotes when the denominator hits 0. Denominator is green function, cosine here. So whenever denominator hits 0, the green function hits 0, we have vertical asymptote. You can check that. Also, whenever the numerator hits 0, the red function here, red is sine, the graph of tangent function, this curve also hits 0. You can easily see that kind of behavior. Okay, those were sine, cosine, and tangent. And let's work out their inverse functions. Of course, they do not have global inverse functions because they are periodic functions and they do not pass a horizontal line test. But if we restrict your domain, then we can make it invertible, kind of like this. For sine function, instead of taking the entire negative infinity to infinity, take the standard domain negative pi over 2 to pi over 2 and highlight that part with thick blue, throw away the other part, de-emphasize them with dashed curve. And the range is negative 1 to 1. Now, what does an inverse function do? X goes to y, y goes to x, vice versa. So domain becomes range, and the range becomes the domain. And consequently, the graph is symmetric with respect to y equals to x, the purple dotted line here. Here is the graph of arc cosine function or inverse cosine function. And the standard domain is 0 to pi this time. And in that domain, cosine function is 1 to 1. Consequently, it is invertible. And the range is negative 1 to 1. And we have this graph of arc cosine function as we see over here in this graph, as red, and blue is cosine function. Okay, here comes the tangent and arctangent functions. Here they are. Tangent function has period pi, and we take the curved part from negative pi over 2 to pi over 2, excluding the endpoints, because at the endpoint we have vertical asymptotes. The function is not well defined. And if we take the range of that, as a matter of fact, this should have been h, range of that range is negative infinity to infinity. So the domain of the arctangent function is negative infinity to infinity, and the range is negative pi over 2 to pi over 2. And how does that translate into the graph? Well, the vertical asymptote, x equal to negative pi over 2 and x equal to positive pi over 2, correspond to the horizontal asymptote, y equals to negative pi over 2 and y equals to pi over 2 for arctangent function. Okay, those are the graphs of arctangent, arccosine, and arcsine functions. Now, how do we use those for trigonometric equations? Well, here is the grand summary. If you have y equals sine of x, then you can solve for x by taking inverse sine of both sides, kind of like this. This is not accurate, it's very formal computation. And we take arcsine of both sides. And inverse sine of sine cancel each other out. So x is equal to inverse sine of y. Well, looks like everything's complete, but there's a bit of a problem. That does not tell the whole story. There is another solution obtained by the symmetry. Pi minus that is also a solution. And we have to add arbitrary 2k pi to capture all the period. Here's a visualization. Arbitrarily selected y value here. This program, by the way, is randomized. See, you have different y value. If you take arcsine, inverse sine, then you're going to get this blue point on the standard domain, which is highlighted in thick blue. But that's not the whole story. The standard domain is negative pi over 2 to pi over 2. And the whole domain is either 0 to 2 pi or negative pi to positive pi. Usually it's more convenient to take negative pi to positive pi so that the full domain includes the standard domain of standard domain where sine function is 1 to 1. And by the symmetry, because the graph of sine function is symmetric with respect to the vertical line x equals pi over 2, pi minus that is also a solution, and that's represented in red in this graph here. Let me draw it a little bit bigger, by the way. Okay, there you go. It's a little bit bigger. And by adding 2 pi or subtracting 2 pi or adding 4 pi and so on and so forth, we have another pair showing popping up in the right hand side and another pair, blue and red, popping up in the left hand side. And then of course, if I move on to the right, another right, we have another pair, and so on. So that's what this 2k pi is doing. We can take this blue and red, solid blue and solid red dots, and then move those pair to the right, and then to the right again, and then to the right again, or also to the left again, and so on and so forth, by taking k value 1, 2, 3, 4, 5, 6, or negative 1, negative 2, negative 3, and so on and so forth. When k value is 0, then we have those solid dots, blue and red. How about arccosine function? Well, here is a graph of arccosine function, and let me make this picture a little bit bigger. Okay, that's better. And if we simply take arc cosine, inverse cosine, okay, we get a solution. That's a solid blue dot positioned inside this thick blue portion of the graph, the standard domain. But cosine function is an even function. So by the symmetry, negative of that is automatically a solution too. That's the red one here, solid red dot, as you can see in this visualization down there. And then of course, cosine function is periodic function, so we need to add 2k pi, where k is arbitrary integer. So 2 pi when k is 1, 4 pi when k is 2, and so on and so forth. So add 2 pi, which means this pair of points, red dot and blue dot, is moved to the right, and then add 2 pi again, then move to the right again, and then add 2 pi again. Okay, that's gonna go outside this picture, but it'll move out to the right again. And if you plug in k value as -1, -2, and so on, then these pair points will move to the left, 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 and so on, and consequently capture everything. This 2k part is pretty much automatic because it is coming from the period. So missing those will not be too much detrimental, and it's really easy to get used to. But the red part, a lot of students miss that one. Pi minus, that is automatically a solution for sine. Negative of that is automatically a solution for cosine. Please remember these because they play a key role in trigonometric equations. Well, we have a little bit of time left, so let's talk about tangent function, which is notably easier. Here's a visualization for tangent. Tangent function has period pi, not 2 pi, so we don't have to worry about the second solution. Just find out with arctangent and just add k pi, and that's it. And the only thing that you have to be a little bit concerned with tangent equation is to remember plus k pi instead of plus 2k pi. That's all there is. Okay, do we have some time for example problems? Looks like we'll have time for one. We have 3 standard problems here: sine problem, cosine problem, and tangent problem. We have time for only one problem, so let's just go ahead with sine problem. So for sine, that's going to be pretty much straightforward. Flip this one to the other side, and we have 3 sine of x is equal to 1. Good. So for sine, so we have sine of x is 1/3. And then what do we get? Take the arc sine, so inverse sine of 1/3. We have one solution. Pi minus of that is automatically a solution. So we have those 2 solutions as we use blue and red color coding as before. And then plus 2k pi plus 2k pi for periodicity. We still have a little bit of time, so okay, let's do cosine problem too. Oh, by the way, is there a graph? Well, that's not really interesting. Too trivial. Okay, let's move on to the second problem. How about the cosine problem? Solve for cosine and then take arc cosine. Remember to take negative of that as well. Here it is. For cosine of x is -3, so cosine of x is -3/4. So x is arc cosine of -3/4, and also negative of that is also a solution. So a good way to capture both is to use plus and minus of those. And of course we have 2k pi because cosine function is periodic with respect to the period 2 pi.